Look up. Look around you, seriously. Whether it's the impressive height of the ceiling above, the solid floor beneath your feet, or the towering skyline reaching for the clouds outside your window, what's the unsung hero that made these structures possible? It's a journey that starts with the immense challenge of gravity and our human ingenuity to overcome it.
Exactly. It's a story of humanity's enduring quest to lift beyond its own physical limits, transforming raw materials into, well, monumental achievements. And often, that story is built around one indispensable machine.
Today, we're taking a deep dive into that intricate world of building, with a special focus on the history and incredible impact of the crane. This isn't just about buildings, it's about the machine that literally built the modern city.
Right.
We'll trace its evolution from ingenious ancient devices, powered by muscle and simple mechanics, all the way to the sophisticated digital tools and management practices that define the towering giant of modern construction.
Our mission for this deep dive is, well, to uncover the fundamental principles, the surprising advancements, and the critical considerations that underpin every construction project that requires lifting. We want to give you a shortcut to being well-informed about the silent workhorses that shape our built world.
And for this deep dive, we've pulled from a truly fascinating array of sources. We've got ancient wisdom from texts like Vitruvius's The 10 Books on Architecture and George Agricola's 16th century engineering marvel De Re Metallica.
And we'll also draw from profound architectural histories like Spiro Kostov's A History of Architecture and Viollet-le-Duc's Lectures on Architecture. And then to bring us right up to the present, we'll consult modern guides on building information modeling, construction management standards, and the detailed intricacies of today's building codes.
It's quite the span of human ambition, really, all centered around that challenge of reaching skyward. Okay, let's unpack this. Our journey to lift heavy things and build incredible structures begins not with modern blueprints or complex software, but with something far more fundamental. Human intuition, careful observation, and, well, a foundational understanding of what simply makes things stand up and stay up.
What's truly surprising here, I think, is how early builders, operating without any of our advanced engineering tools or computational analysis, still managed to arrive at principles of stability and, crucially, forms that were aesthetically pleasing. Vitruvius, for instance, speaking on the role of the architect in antiquity. He suggests that successful building was never just about the craft itself.
So you're saying ancient architects were far more than just master builders. Vitruvius highlights that an architect needed an incredibly broad knowledge base, encompassing things like geometry, astronomy, even music, just to pass judgment on tasks. It sounds like they expected a polymath for every single job.
Pretty much. It really points to a deeply multidisciplinary approach to building, even way back then. Especially when you think about the immense challenge of raising massive stones without, the kind of machines we have today.
Right, without a tower crane sitting there.
Exactly. That multidisciplinary approach wasn't just theory, it actually shaped the physical structures we still admire. The ancient Greeks, for instance, took that holistic view and encoded it into highly structured yet beautiful architectural orders, like the Doric or Ionic columns. Viollet-le-Duc points out that all parts were in necessary places, designed to satisfy both reason and senses, aiming for what he calls an ideal perfection.
Ideal perfection.
Yeah, and he explains that this ideal was achieved through fixed relative proportions, which remained constant regardless of the building's overall size. So whether a portico was, say, 30 cubits or 10 cubits high, the internal ratios of its columns and the bits above them, the entablature, wouldn't change.
Okay. So it was all about the ratio, not the absolute size.
Precisely. It shows a deep, almost philosophical commitment to harmony and order, even when faced with the practical difficulties of lifting and placing those heavy components correctly.
That's a great point about how beauty wasn't just about math. It was about how the human eye perceived those proportions.
Yeah.
Viollet-le-Duc also touches on this theme. He notes that the eye comprehends dimensions by contrasts.
Yes, exactly.
A church nave, for instance, appears much loftier if it's narrow in proportion to its height. He even mentions the Egyptian triangle as a kind of perfect standard that helped architects avoid what they considered identities of widths and heights, which they apparently found displeasing.
It's like they had an early grasp of optical illusions, almost, and how to manipulate them for aesthetic impact, making structures feel grander than they perhaps strictly were. It's quite sophisticated when you think about it.
Definitely. And that focus on grand, imposing structures extended to the Romans, who developed their own distinct architectural character. Viollet-le-Duc credits Roman architecture's principal merit to the judicious employment of materials.
Judicious employment. I like that.
Yeah, their buildings demonstrated immense power and intelligence, leaving profound impressions through their sound reasoning and grand conception. It wasn't just about aesthetics for them, it was about mastering the physical world to create structures that endured and projected authority. And often, that involved finding new ways to handle massive materials, figuring out how to lift them into place.
So, the truly surprising takeaway here, maybe, is that even without advanced engineering tools, ancient builders were profound polymaths, blending art and science intuitively. Their structures weren't just strong, they were designed to feel right to the human eye and soul.
A holistic approach to conquering gravity that, still forms the bedrock of design today.
Yeah.
But what did they actually build with to achieve these feats? And how did those early societies adapt their methods, especially for lifting and placing large components, to the materials at hand and their local environment? It's easy to forget that sophisticated material science is a relatively modern invention.
Right, that's a great question. It raises this important point about the fundamental interplay between available resources and evolving building techniques, particularly how they handled heavy loads. Kostov, in his A History of Architecture, tells us that early community architecture was often quite simple.
Like huts and basic houses.
Pretty much. Houses were initially elliptical, then rectangular and apsidal, typically just one-room detached structures made of mud brick on stone or rubble foundations, very direct, local, resource-driven, probably built mostly by hand, without needing complex lifting gear.
That makes sense. You build with what you have readily available. But then we see that Roman influence popping up even in places like monasteries later on.
Yeah, Viollet-le-Duc points out that monasteries, which were quite significant community structures requiring more substantial construction, were often located on former Roman sites. Their plans were even influenced by the layout of the Roman villa.
Really? So they were kind of adapting old structures.
Or at least the ideas of those structures. He notes that their building programs prioritize things like aspect, which way it faced the site itself, and practical requirements over strict symmetry. This led to a judicious and well-arranged agglomeration of buildings. They adapted existing large-scale techniques to new needs, presumably including how they managed construction and maybe some basic lifting.
A fascinating example of adaptive reuse and architectural lineage. But not all materials were equally cooperative,
Yeah.
right? Which would certainly impact how you'd even think about lifting or shaping them.
Oh, absolutely. Clifton Taylor highlights that certain stones, like Mendip limestone in Somerset, were notoriously resistant to chisels. Very hard stuff. This made detailed carving and undercutting extremely difficult.
So forget fancy decorations then.
Pretty much. Consequently, it was deemed unsuitable for elaborate ornamentation. The material itself dictated the art and likely how it could be handled and lifted. You probably wouldn't want to hoist a huge uncarvable block unless absolutely necessary.
That's a fantastic insight into how geology shaped aesthetics. But beyond these natural limitations, did they also start thinking about artificial ways to get around material constraints, perhaps driven by cost and the desire to build more efficiently? Easier lifting, maybe.
Precisely. And speaking of practicality, Clifton Taylor also describes an early awareness of economical alternatives. Large slates, colored to resemble brick or stone, were used as an economical substitute for finely jointed ashlar masonry that's essentially perfectly cut, squared stones fitted together precisely.
Like fake stone siding, but from the 18th century.
Sort of, a technique seen at places like Soho House around 1797. This shows an early drive for efficiency, perhaps using lighter, easier-to-handle components, foreshadowing mass production.
And that drive eventually led to widespread adoption of materials like brick, didn't it?
Yes, the economies of brickmaking, combined with the inherent fire-resisting character of brick, made it an increasingly practical and prevalent building material. It was easier to produce in standard sizes, easier to transport, and much easier to lay by hand than massive cut stones.
Less heavy lifting per unit.
Exactly, offering both affordability and safety benefits that were increasingly valued, especially in dense urban environments prone to devastating fires.
So the real insight here is that the earliest builders weren't just skilled craftspeople. They were master problem solvers, continuously adapting their methods and materials to overcome the inherent challenges of lifting and placing, often with surprisingly sophisticated understanding of geology and economics.
It's a continuum of innovation that continually reshaped our built world, laying the groundwork for how we would eventually build much, much larger structures, requiring much more sophisticated lifting.
Okay, when it came to grand, enclosed spaces, especially those requiring massive spans and immense heights, the Romans truly pushed boundaries. They didn't just build big, they created monumental spaces that demanded innovative lifting and construction techniques.
You're absolutely right. Their mastery of materials, particularly concrete, allowed them to create structures of immense power and scale. And these provided inspiration and structural lessons that would last for centuries. Spiro Kostov illustrates this beautifully when discussing the interior of St. Foy's Abbey Church.
Straightforward, right.
Its tall, vaulted naves, supported by these thickly grouped cluster piers, represented a significant architectural novelty for its time. He even compares it in power and scale to Hagia Sophia in Istanbul,
Wow, that's high praise.
which he describes as a Christian rendition in brick of the prodigious concrete shells of late Roman build. So you see this clear lineage. The Romans' large-scale construction, with all its inherent lifting challenges, directly influenced subsequent builders hundreds of years later.
That's incredible. You see the direct lineage of ambition of trying to enclose these vast spaces. And Viollet-le-Duc provides a detailed look at how the Romans achieved this, specifically with the Basilica of Constantine.
A massive structure.
He describes its construction using rubble work with brick facings coated with stucco. But the central nave was where the real innovation lay, featuring these enormous groined vaults built from a concrete mass.
And this concrete mass, it's important to remember, being essentially inert and without elasticity, like, say, timber or steel, posed a unique structural challenge. The Romans, probably through a lot of trial and error, learned to manage it.
How so?
Well, Viollet-le-Duc emphasizes that it required substantial buttresses, those external supports you see on cathedrals, to prevent collapse. The Romans understood that even their massive concrete structures, seemingly indestructible, needed active resistance to prevent their immense weight from causing cracks and eventual failure. The vaults wanted to push outwards, and the buttresses push back.
That's a crucial insight. The Romans, in their ambition to build colossal concrete vaults, stumbled upon a fundamental paradox. Even the heaviest materials need active opposition to stand tall. Sheer mass alone isn't enough. You need to manage the forces.
Exactly. It's a lesson echoed in every modern skyscraper's bracing system, and actually in every crane carefully balancing its load against a counterweight.
That's a great connection. And speaking of supporting immense loads, Palladio, in the 4 books of architecture, highlighted the absolutely critical importance of foundations, specifically pilings.
Yes, a point often overlooked, but so vital. He argued that pilings were needed under both exterior and interior walls, not just the outer perimeter.
Why both?
His reasoning was sound. If central foundations are different from outer ones, for example, if only the outer walls are piled deep into stable ground, then you can get differential sinking. One part settles more than another.
Which leads to cracks.
Exactly. Cracks, structural damage, and potentially the ruin of the entire edifice. He strongly advocated for the value of trifling expense in piling to avoid such catastrophic failures later on. A timeless lesson in the importance of a stable base for any heavy structure, and certainly for the cranes that might build it.
Which reminds me of a principle in modern construction management, especially for projects involving enormous loads or tall structures. The PMBOK guide, the project management body of knowledge. It stresses the importance of tailoring. It highlights that the deliberate adaptation of approach, governance, and processes to the unique objectives, stakeholders, and complexity of the environment is crucial for project success.
So tailoring the plan to the specific job.
Right. Factors like the business environment, the size of the team, the level of uncertainty, they all influence how project systems are tailored. And this mirrors the adaptability we see in ancient building, where materials and methods and the crucial challenges of lifting were tailored to local conditions and available resources.
That's a great parallel. Whether it's the Romans adapting their concrete techniques to build unprecedented vaults, or a modern project team tailoring its management approach to safely lift multi-ton components with a specific crane, the core idea is about intelligent, context-specific problem solving in the face of immense forces and challenges.
As we move through history, say into the Middle Ages and the Renaissance, we see builders and architects developing more explicit, almost scientific understandings of how structures work and how to handle increasingly massive components. It feels like a crucial shift from purely intuitive understanding to more codified knowledge, pushing the limits of what could be lifted and built.
Absolutely. This era represents a crucial shift from that empirical, learned-by-doing knowledge to a more theoretical and analytical approach. The Gothic cathedrals are maybe the prime example of this complex evolution. J.E. Gordon, in his fantastic book Structures or Why Things Don't Fall Down, marvels at how master masons of the High Middle Ages created Gothic buildings with immense structural and artistic achievement.
They are breathtaking.
They are, and he notes that while they lost, as he puts it, any visible connection with its classical origins, the line of descent is clear and simple structurally. This suggests a continuous, if transformed, understanding of how to distribute immense weight, how to get forces down to the ground safely.
So even though they looked completely different from Roman basilicas, all pointed arches and flying buttresses, the underlying physics were essentially the same, just applied in new, daring ways to create incredibly tall and seemingly delicate structures.
Exactly. Gordon also makes a really clear point about a fundamental choice: roof support. He says that using beams, simple horizontal elements, was generally much cheaper and simpler than using arches.
Why is that simpler?
Because beams, he explains, transmit weight vertically downwards into the masonry walls, straight down. Arches, on the other hand, create a sideways and outwards push, a thrust, which can cause unwelcome disturbance to the walls if not properly counteracted, usually with buttresses.
Ah, okay. So beams are simpler forces, arches are more complex.
Right. It's a basic but powerful distinction that must have guided countless decisions, particularly when trying to figure out how to lift and place heavy roof elements without destabilizing the whole structure.
Makes sense. And beyond just the type of structural element, the actual performance of the materials themselves was being better understood, even if not through modern scientific testing methods.
Definitely. Gordon provides some very telling figures on material performance, contrasting how much punishment different materials can take before breaking what engineers call work of fracture and tensile strength.
Okay.
Imagine glass or pottery, a tiny impact, low energy, and it shatters, very low work of fracture. Mild steel, on the other hand, has vastly higher values. It can absorb a massive amount of energy, bending and deforming long before it actually gives up and breaks.
Which is why we eventually started building skyscrapers with steel frames, right?
Precisely. We needed materials that could withstand immense loads, the stresses of being lifted high into the air, assembled, and handle wind forces, not just gravity. Pottery columns wouldn't quite cut it.
No, probably not. That's a huge difference. It really emphasizes why certain materials were chosen for certain applications, even if it was through trial and error over centuries.
Yeah.
And then we have Palladio again, offering what seemed like a simple rule, but with structural implications, specifically for load distribution.
Ah, yes, Palladio and symmetry. James Ackerman, discussing Palladio's work, notes his rule that rooms on the right side of an entrance should correspond and be equal to those on the left.
Seems like just an aesthetic preference for balance.
Well, Palladio apparently believed this ensured walls would sustain the weight of the roof equally, preventing instability caused by unequal masses pushing down. Ackerman, however, points out that this was an early and perhaps, as he says, feebly explained engineering principle.
So not entirely accurate.
It was consistent with Palladio's own practice, but the engineering explanation only really applied to certain types of roofing systems. If you applied it universally, Ackerman notes, it could lead to some pretty impractical designs, like a ridiculously peaked roof for Palazzo Chiricati. It highlights the evolving nature of structural theory, how the understanding of lifting and load distribution was constantly being refined.
It's fascinating how a seemingly aesthetic rule had structural roots, even if imperfectly understood at the time. For illustrative content, just think of the soaring, seemingly delicate vaults of a Gothic cathedral. They appear almost weightless, but they're a testament to a deep, evolving understanding of force and material and the incredible human effort, sometimes involving early lifting machines we're only now rediscovering, required to get those massive stones hundreds of feet into the air. Okay, here's where it gets really interesting, I think, especially for our focus on lifting. While not directly about building massive structures like cathedrals, we find a fascinating glimpse into humanity's earliest attempts at mechanical lifting in George Agricola's 1556 text, De Re Metallica.
Ah, Agricola. Yes, this is a fantastic source.
This is about pushing the boundaries of human physical limits, developing actual machines long before we had dedicated construction cranes as we know them.
And this is where it gets truly fascinating, because in his 1556 text, De Re Metallica, which is mostly about mining and metallurgy, we find descriptions of truly ingenious machines. These directly show humanity's persistent drive to overcome physical limitations through mechanical advantage. Agricola describes a machine specifically for lifting water and ore out of mines. designed to replace human treading, literally, people walking inside wheels, with a water wheel whose paddles are turned by the force of the stream.
So harnessing natural power for heavy work, that's a significant step beyond pure muscle power or even animal power. What were the key components of this early water-powered lifting machine?
Agricola meticulously details it. The machine consists of an axle, a drum around the axle with clamps, a chain running over it, and dippers or buckets attached to the chain. It also includes something called a balance drum, probably a form of counterweight or flywheel.
Wow, that sounds surprisingly complex for the 16th century.
It is. It's a clear illustration of early mechanical engineering principles at work. Gears, chains, scoops, power transmission, all integrated into a functional system. It's essentially a crude but effective multi-stage lifting device powered by nature, a direct ancestor to the powerful hoists and, yes, cranes we see today.
A truly complex system for its time, showing real ingenuity. He also mentions its capacity, but also some significant challenges, right? It wasn't perfect.
No, definitely not. This particular design, which Agricola calls the third machine, was superior in capacity. It had much more capacious dippers than other designs he described, so it could lift more material per cycle. However,
There's always a however.
there often is. Agricola notes that the dippers were frequently broken. Reliability was a major issue, and this often led miners to prefer other, perhaps less powerful but more dependable methods.
So practicality won out over raw power sometimes.
Exactly. They often opted for lifting small quantities of water by the first 5 machines or to draw it up by suction pumps, or for larger quantities, they used the rag and chain pump or to bring it up in water bags. It highlights a very practical consideration. Reliability and maintenance often outweighed sheer lifting power in these early mechanical solutions. It's a tension that continues even with modern, complex cranes. Downtime is incredibly costly.
That's a really pragmatic lesson, isn't it? Reliability over brute force. The big aha moment here, I think, is that this 16th century mining machine, with its water wheel, gears, chains, and scoops, is a direct ancestor to the complex mechanical systems we see in modern construction equipment. It showcases our enduring, centuries-old quest to lift heavy things and conquer gravity, setting the stage for the true cranes that would emerge during the Industrial Revolution. Okay, moving into the Industrial Revolution now, the very materials we built with were profoundly transformed. This allowed for entirely new scales and types of construction, literally enabling us to build bigger, higher, and faster than ever before, and this, of course, demanded much more powerful lifting machines.
This era marked a profound shift, no question. The advent of standardized, mass-produced, and much stronger materials, particularly iron and then steel, empowered engineers to conceive and construct much larger and more complex structures. Kidder, Parker, and Ching provide detailed specifications for structural steel beams, joists, and girders that emerged during this period.
So standardized parts.
Exactly. These components had defined dimensions and, crucially, defined engineering functions. Engineers knew their moment of inertia, section modulus, radius of gyration, all these critical properties related to bending strength, resistance to twisting, buckling resistance. This was no longer intuitive building. It was precise, calculable engineering.
Which must have given designers incredible confidence.
It did, and it allowed for the components themselves to be engineered for safe lifting and handling. You knew the weight, you knew the strong point.
That's a huge jump from stone and timber, where every piece is unique. It meant that every part of the steel frame could be designed with incredible precision, knowing exactly how it would perform under stress, and also how it could be hoisted into place.
They even developed detailed design considerations for things like riveted plate and box girders, these huge built-up structural elements, including methods for their design and analysis of deflection under load. This allowed for the creation of truly massive structural members that would become the backbone of early skyscrapers, bridges, and factories, things impossible to build without correspondingly massive lifting capacity.
And this evolution continues to this day, right? We're still innovating with materials.
We are. Interestingly, the 2021 International Building Code, IBC, saw a significant expansion of what's called Type 5e construction, specifically for mass timber production techniques.
Mass timber, like engineered wood.
Exactly. This new category includes building elements made of engineered timber or non-combustible materials, but they still require specific fire resistance ratings. It shows that even as we embrace new materials and methods, the core principles of structural integrity and safety remain paramount. And often, these new methods involve lifting ever larger prefabricated components.
It's fascinating how building codes evolve to incorporate new technologies like that. And then there's the prefabrication of these massive components, which dramatically streamlines the construction process, but places huge demands on lifting.
Absolutely. Fundamentals of building construction describes the use of precasting beds for fabricating things like very long A-ish toe girders. These are those massive, standardized concrete beams you often see supporting highway bridges. Huge things.
How do they even handle those?
Well, the book describes how they include depressed pre-stressing strands held by steel pulleys and mild steel reinforcing bars for stirrups inside the concrete form. And then, crucially, vertical twists of pre-stressing strand are embedded to serve as lifting loops once the concrete cures. Purpose-built attachment points for cranes.
Ah, designed for lifting from the start.
Precisely. This ability to prefabricate and then safely handle these colossal components hinted at the future of large-scale construction and the specialized purpose-built cranes needed to put them in place. This shift from on-site, piece-by-piece construction to off-site, large component fabrication dramatically changed the logistics and possibilities of building, paving the way for the high-rises and massive infrastructure projects we see today, all utterly reliant on increasingly powerful and sophisticated cranes.
So we've gone from simple mud brick dwellings to massive steel and concrete components, all guided by evolving structural understanding and increasingly powerful lifting machines. But modern construction isn't just about sheer strength or lifting capacity anymore. It's increasingly about performance, efficiency, and sustainability.
This is where we see how a scientific understanding of materials and environmental factors becomes truly paramount. It leads to structures that are not only resilient and strong, but also responsible in their energy consumption and overall environmental impact. For instance, modern concrete technology has evolved far beyond its Roman ancestors, or even the concrete used just decades ago.
How so?
Francis D.K. Ching notes that contemporary concrete often uses admixtures, things added to the mix, like glass, steel, or polypropylene fibers to reduce shrinkage cracking, which is a common problem. Other additives can increase surface hardness and abrasion resistance, tailoring the material for specific performance needs. This means even the most demanding structural components, the ones that need to be lifted high up, can be made more durable and reliable.
That's a significant advancement, tackling those common issues with concrete. And proper moisture management, especially for large concrete slabs on the ground, is absolutely critical too, right? You don't want water coming up from below.
Absolutely critical. Ching also highlights the importance of a usually 6 mil thick polyethylene moisture barrier placed under concrete slabs on grade. This barrier is often covered by a protective sand layer, which helps absorb excess water during the concrete curing process and, crucially, prevents the capillary rise of groundwater up into the slab over the life of the building.
Because that moisture can cause all sorts of problems.
Serious durability issues, yeah. From mold growth to structural degradation of finishes or even the slab itself, compromising the integrity of components that might have been lifted into place with great effort and expense.
And it's not just the foundations. The entire building, envelope the walls. The roof is becoming a real science.
Oh, completely. Joseph Saberic's Builder's Guide elaborates on advanced exterior air barrier systems. These aren't just simple house wraps anymore. They use specialized wraps with carefully taped joints, sill gaskets under walls, building paper under bottom plates. Even polyethylene in the ceiling can be part of this integrated air barrier system.
Why is controlling airflow so important?
It's all crucial for preventing air transport of moisture, which is actually a leading cause of building envelope failure, much more so than vapor diffusion. Keeping unwanted air in the moisture it carries out while allowing the wall to dry if it does get wet, that's the goal. These meticulous details ensure a building performs efficiently and durably no matter how tall it is or how it was assembled by cranes.
Indeed. It's a holistic approach to creating a tight, energy-efficient building. And complementing this, you need control inside too, right?
Yes. Effective control of interior moisture levels year-round is typically achieved through mechanical ventilation, bringing fresh air in controllably, and, during cooling periods, dehumidification. This integrated approach ensures good indoor air quality and comfort while minimizing energy waste. It leads to structures that are high-performing long after the construction cranes have left the site.
This sounds like a lot of individual technical decisions, but it all adds up to something bigger. This push towards sustainable building.
Exactly. You see it formalized in things like the U.S. Green Building Council's USGBC LED program leadership in energy and environmental design. It offers various certification levels, certified, silver, gold, platinum across categories, focusing on energy efficiency, water conservation, waste reduction, material selection, and human health impacts.
And LEED certified buildings are actually shown to save energy, conserve water, and even boost employee productivity, right?
That's the evidence, yes. And some initiatives push the boundaries even further. The Living Building Challenge is an incredibly rigorous standard. It mandates that a building must produce as much energy as it consumes annually, provide all of its required water through captured precipitation or recycling, and process all its sewage on site.
Wow, that's demanding.
It really is. Projects like the Bullitt Center in Seattle demonstrate this.
Yeah.
They even went so far as to source heavy materials like steel, concrete, and wood from within a 300-mile radius to drastically reduce the embodied carbon footprint associated with transportation. It's a truly holistic and demanding approach to sustainability, where every single material choice, including those heavy ones that need lifting, is scrutinized for its impact.
And there's also the 2030 challenge, which is more of an industry-wide goal.
Yes, an initiative for architects and the building sector to commit to designing carbon-neutral buildings, meaning they use no fossil fuel energy to operate by the year 2030. It's a recognition of building significant energy consumption and carbon emissions and a collective effort to change that.
So what stands out here is that from managing moisture in a simple concrete slab to sourcing local timber for a massive frame, every design decision today has a ripple effect on a building's long-term performance and environmental footprint. The ability to lift and place components efficiently and sustainably is now a core part of this increasingly scientific approach to building. Okay, as structures grew taller, more complex, and more densely packed into cities, the need for rigorous, standardized rules became absolutely paramount. You can't just wing it when you're building a 50-story skyscraper or operating a giant tower crane right next to another building in a crowded downtown core.
Absolutely not. And this raises that important question. How do we ensure not just functionality, but also public safety, structural integrity, and resilience against hazards like fire in our ever-evolving built environment? Building codes provide that critical framework.
They're not just suggestions, they're the law.
Exactly. The Building Codes Illustrated Guide shows us that allowable building heights and areas, for example, are carefully determined by multiple factors. It's not arbitrary. It depends on the construction type, like Type I non-combustible, Type V wood frame, or the new Type 5V mass timber we mentioned.
Mm-hmm.
The occupancy classification, is it an office, a hospital, residential, and crucially the presence or absence of automatic sprinkler systems. These aren't arbitrary rules. They're based on extensive analysis of fire spread, structural stability under fire, and evacuation times. These are especially critical when coordinating complex lifting operations over populated areas below.
So a concrete building will have different height and area allowances than a wood-framed one, which makes perfect sense from a fire perspective. And fire resistance itself is a massive factor, often dictating the materials that can be used and how they're assembled, right down to the details.
It truly is. Strict requirements exist for the fire resistance ratings, usually measured in hours of structural members like beams and columns, as well as entire assemblies like walls and floors. These ratings must comply with the specified type of construction and be complementary to the assemblies they support. You can't have a 2-hour rated floor supported by 1-hour rated beams, for instance.
Right. The weakest link determines the overall strength.
Precisely. And crucially, the code explicitly prohibits service elements like pipes or electrical conduits from being embedded within the required fire protection coverings of structural steel, for example, because those pipes can conduct heat right through the protection and cause the steel to fail prematurely.
That's a critical safety detail many might not think about. It's incredibly granular. Beyond fire, accessibility is also a key modern concern, ensuring that these tall buildings are usable and safe for everyone.
Yes, very important. Per the IBC, accessible spaces within a building must have an accessible means of egress, a safe way out for people with disabilities. If more than one means of egress is required by code, which is common in larger buildings based on occupancy load, then at least 2 accessible means of egress must be provided in new construction.
So, multiple options for safe evacuation.
Yes, ensuring that people with disabilities have safe and independent routes out of a building during an emergency, even from high floors. This might involve areas of refuge or specially protected elevators.
And some buildings, especially the super tall high-rises, are taking this even further with special elevator systems, which are themselves marvels of vertical transport, almost like internal cranes designed for moving people rapidly.
Exactly. In super tall high-rise buildings, often found outside the United States currently, occupant evacuation elevators are specifically designed for self-evacuation by occupants. These offer increased access for persons with disabilities and must be hardened, meaning protected against fire, smoke, water, and power loss to ensure continuous performance during emergencies. It's a testament to how safety engineering continues to adapt to new architectural ambitions, ensuring that the incredible heights achieved by modern construction and lifting technology are also incredibly safe.
And it all starts from the ground up, literally. The foundation needs to be right,
Yep.
especially if it's supporting a massive tower and the cranes needed to build it.
Absolutely. The fundamentals of residential construction reminds us that for sites where the natural soil is insufficient to support a building's load, which is quite common, then engineered or compacted fill is required.
So bringing in better soil.
Essentially, yes. It involves placing soil or crushed rock in layers, typically 6 to 12 inches deep, called lifts. Each lift is then compacted mechanically to a specific density before the next layer is placed. The moisture content of the soil is carefully monitored and controlled during this process, as it critically affects how well it compacts. This creates a stable, man-made platform capable of supporting the structure and, just as importantly, the heavy construction machinery like cranes that will operate on the site during construction.
So building codes aren't just arbitrary rule books. They're the accumulated wisdom of centuries of construction experience and scientific testing, continuously updated to integrate new materials, new technologies like mass timber, and new safety standards, particularly as we build taller and rely on powerful machines to lift ever greater loads. These specific details reflect how evolving materials and construction methods are continually integrated into these crucial regulatory frameworks, aiming to ensure safety and performance for every new building that rises, often with the help of incredible cranes. Okay, from drafting tables with T-squares and pencils to dynamic digital models on computer screens, technology has utterly transformed how we design, plan, and coordinate construction projects, particularly those involving complex structures and intricate lifting operations. The pen and paper days feel like ancient history now.
Oh, completely. What's truly fascinating here is how digital tools like Building Information Modeling, or BIM, allow for unprecedented levels of integration, analysis, and collaboration. They help tackle complexity and identify potential issues long before physical construction even begins.
So what is BIM exactly? It's more than just a 3D model, right?
Much more. The CMAA Construction Management Standards of Practice and Jumpstart define BIM as a database-driven modeling system designed specifically for collaboration. Unlike traditional 3D CAD, which is mostly just geometry, each element within a BIM file, a wall, a beam, a window, a duct, even a crane model perhaps carries attached information.
What kind of information?
Things like construction details, material properties, performance characteristics, product specifications, manufacturer data, cost, schedule information. It makes the model incredibly rich with data, including details that are vital for planning complex crane lifts, like component weights, center of gravity, and required clearances.
So it's not just a drawing, it's an intelligent database representing the entire building, which can even model how its components will be lifted and assembled.
Exactly. The BIM handbook further explains that BIM design applications are founded on object-based parametric modeling. This means objects have relationships with each other. If you change the height of a floor, the walls connected to it automatically adjust. This greatly facilitates model creation and editing and significantly reduces the likelihood of coordination errors.
That's a key advantage, especially when you're coordinating the movement of massive components with cranes. Fewer errors means safer and more efficient lifts. However, are there still challenges?
Oh, yes. A major challenge remains what's called platform-to-platform exchange or interoperability. Getting different software platforms, say an architectural design tool like ArchiCAD or Revit, and a structural steel fabrication platform like Tekla or StriCAD, to seamlessly pass editable models back and forth, especially models with complex embedded rules for object integrity, is still an ongoing hurdle.
I can imagine. Trying to get different specialized software to talk to each other effectively is always a challenge in any industry. But the analysis capabilities of BIM sound truly transformative, especially for planning crane operations.
They really are. BIM supports both qualitative and quantitative analyses for building performance. This includes simulations for things like structural integrity, temperature control, ventilation and airflows, lighting, pedestrian circulation, acoustics, energy distribution and consumption, water supply, and waste disposal.
So you can test the building virtually.
Pretty much. These simulations allow designers to predict how a building will perform long before it's built, optimizing for efficiency, comfort, and safety. And crucially, this digital environment allows for the precise planning of how large mechanical systems, including the cranes themselves, will interact with the structure during the construction phase. You can model the crane's reach, capacity, and potential obstructions.
That's incredibly powerful. And one of the most practical applications I've heard about is clash detection, which seems especially vital for avoiding mishaps with heavy equipment like cranes.
Clash detection is indeed a key BIM process and a huge benefit. It uses the 3D models from different disciplines, architectural, structural, mechanical, electrical, plumbing, sometimes even the crane path, to automatically check for interferences by searching for intersecting volumes.
Finding where things literally run into each other in the model.
Exactly. This often involves combining and clashing multiple models from these disparate sources in a common software environment. It allows teams to identify mistakes like a pipe running through a structural beam or a crane's boom potentially clashing with an adjacent building during a lift before these mistakes ever reach the physical construction site.
That must save tremendous time, money, and prevent potentially dangerous errors in the field.
Absolutely. It's a huge benefit right there, catching problems virtually when they're cheap and easy to fix, rather than discovering them physically when they're expensive, cause delays, and pose safety risks. And BIM goes even further than just 3D modeling and clash detection, with concepts like 4D and 5D BIM.
4D and 5D. What do those dimensions represent?
So 4D schedules dynamically link the project's critical path method, CPM schedule activities, and the timeline directly to the 3D BIM objects. This provides a graphically rich and animated representation of the planned construction sequence over time.
So you can literally watch the building being constructed on screen, timeline included, see the cranes moving.
Precisely. You can visualize the entire build process, including the movement and placement of every major component by the cranes, well before anything is actually built. It's an incredibly powerful tool for planning phasing, coordinating trades, optimizing crane locations and usage, and running what-if scenarios for different construction sequences.
That's amazing visualization. And 5D, is that cost?
Yes, 5D cost management builds on this by enabling the attribution of resources and their respective costs to every element in the BIM model. This allows for parametric and dynamic quantity takeoff. For materials, the computer calculates quantities automatically from the model, resulting in more accurate and faster cost estimates. It shifts the estimator's focus from tedious manual quantity counting to actual cost analysis, value engineering, and accurately accounting for the costs associated with lifting, transporting, and installing every piece.
It sounds like a complete digital ecosystem for planning and managing construction. The big takeaway here seems to be that digital tools like BIM are essentially sophisticated flight simulators for construction, allowing us to build and rebuild structures virtually, identify challenges like crane paths or material clashes, and optimize every lift before the first shovel hits the ground.
That's a great analogy. This level of digital transformation is profoundly changing the planning and execution of projects, making taller, more complex structures feasible and hopefully safer to build. And it's all pointing towards a future where the buildings themselves become smart.
Smart buildings.
Yeah, the city of tomorrow explores this idea, suggesting that with ubiquitous computing, our urban life increasingly converges physical and digital space. Buildings themselves could potentially transform into intelligent agents with the capacity to learn from and coexist with their occupants, becoming, as the book says, connective tissue between bits and atoms. A fascinating, if slightly unnerving, prospect.
All this incredible design and cutting-edge technology, all these powerful cranes reaching for the sky, it means absolutely nothing without the skilled people and the meticulous processes needed to bring it all to life safely and efficiently. It's one thing to design it on a computer, another to build it in the real world, and an entirely different thing to manage the complex choreography of giant machines, materials, and hundreds of workers.
That's the absolute truth. At the end of the day, successful construction is fundamentally about managing incredibly complex, time-consuming undertakings. It requires strategic planning, relentless coordination across diverse specialized services designers, engineers, surveyors, fabricators, dozens of subcontractors, crane operators.
The list goes on.
It does, all the way from the initial inception of an idea through to final completion and handover. The CMAA Construction Management Standards of Practice outlines that a total project effort is normally broken into several distinct phases. Pre-design, design, procurement, buying things and hiring contractors, construction itself, and then post-construction or closeout.
A logical life cycle.
Mhm.
And each phase has its own specific goals and challenges,
Yeah,
right?
exactly.
Especially for orchestrating those critical heavy lifts.
Exactly. And before any physical work even begins, a critical document is developed to guide the whole
A
process.
master plan.
Essentially, yes. Prior to construction, a project-specific construction management plan is developed. This plan clearly identifies the roles, responsibilities, and authority of the project team, who does what, who reports to whom, and it outlines all the procedures to be followed during construction. This includes things like communication protocols, quality control measures, safety procedures, and very importantly, detailed lift plans for cranes and other heavy equipment. This sets the stage for how everything will operate, aiming for safety and efficiency.
So the construction manager, or CM, plays a central role in this complex orchestration, acting almost like the conductor of a very large, very complicated orchestra.
That's a perfect analogy. The CM provides leadership and coordination, acting as a central hub for communications with all the design professionals, contractors, suppliers, and often the owner to ensure project requirements are met according to the plan. This centralized communication flow is essential to avoid misunderstandings, resolve conflicts quickly, and keep everyone aligned, particularly when critical, high-risk lifting operations are underway.
And good communication means good meetings, presumably? What are the different types of meetings typically involved in managing a complex build, especially when large equipment like cranes are a major factor?
CMAA outlines three basic categories. First, you have pre-construction meetings. These are held before work starts to orient the contractors to the specific project procedures, site rules, safety requirements, and site utilization plans, like where cranes will be set up, where materials will be stored, access routes, etc.
Getting everyone on the same page from day one.
Exactly. Then you have regular progress meetings. These are typically scheduled weekly, bi-weekly, or maybe monthly, depending on the project pace. Their purpose is to monitor compliance with schedules, coordinate the efforts of different trades, identify upcoming issues, and facilitate short and midterm planning, like coordinating the sequence of crane lifts for the next couple of weeks.
Keeping things moving.
Right. And finally, you have special meetings. These are called on an as-needed basis to resolve immediate problems or discuss detailed topics that aren't really suitable for the broader progress meetings. Maybe there's a complex technical issue with a crane lift or a specific coordination problem between two subcontractors that needs focused attention.
So a very structured approach to communication designed to keep everyone informed and the project on track. And a fundamental tool for managing those schedules, especially for a complex sequence of interdependent tasks like crane lifts, is the critical path method, or CPM.
The critical path method is indeed a fundamental scheduling tool, as Daniel Halpin's construction management highlights. It's a network-based technique used to calculate the critical sequence of activities, those specific tasks that, if delayed even by a day, will delay the entire project completion date.
So you know exactly which tasks have no room for error.
Correct. And it also calculates the leeway, or float, the amount of time a non-critical activity can be delayed without impacting the overall project finish date. CPM is essential for coordinating resources like cranes and crews, estimating financial requirements over time, assessing the potential impact of delays, and developing strategies to recover lost time. When you're talking about expensive resources like heavy lift cranes, understanding which activities involving them are on the critical path is absolutely paramount for cost and schedule control.
That sounds incredibly useful for large, complex projects.
Yeah.
Are there other scheduling methods used for different types of projects, perhaps where cranes are working in a more repetitive pattern?
Yes. Halpin also mentions linear scheduling, sometimes called line of balance scheduling. This is particularly useful for projects that have a predominant geometric direction. Think vertically linear projects like high-rise buildings, where work progresses floor by floor, or horizontally linear ones like roads, tunnels, pipelines, and bridges.
Where the work moves along a line.
Yes, exactly. It's also very effective for projects with highly repetitive tasks, like pouring successive floor slabs in a tall building or placing similar precast panels floor after floor. Linear scheduling visually represents the rate of progress for different crews or activities, making it easier to optimize the workflow and ensure continuous, efficient use of resources like cranes.
It really does sound like conducting an orchestra. Each instrument, each subcontractor, each crane playing its part, meticulously timed and coordinated by the CM to produce the final symphony of a completed building. The cranes are like the powerful soloists, lifting the grandest notes into place precisely when needed. That's the art and science of construction project management. Now, beyond the purely technical aspects and the incredible machines like cranes, building is also deeply human. It involves a multitude of different people. The owner paying the bills, the designers with the vision, the engineers making it stand up, the builders putting it together, the suppliers delivering materials, the regulators checking compliance, and often the surrounding community dealing with the disruption, all with varied interests and expectations, especially when a giant crane is operating right in their neighborhood for months on end.
That's such a crucial point. What's fascinating here, and increasingly recognized, is how vital human interaction, effective communication, and genuine stakeholder engagement are to navigating these complexities and ensuring what the PMBO guide calls a collective shaping of a shared solution. It's about much more than just transmitting information downwards or ticking boxes.
So it's about building relationships,
Right.
not just
Yeah.
buildings.
In a very real sense, yes. The PMBO guide emphasizes that identifying, analyzing, and then proactively engaging with stakeholders from the start to the end of the project helps to enable success. You can't just wait for problems or complaints to arise.
That proactive part seems key, doesn't it? Not waiting for the phone to ring with an angry neighbor, but anticipating interests and needs, particularly when a project has such a visible impact, like a tall building going up with a massive crane.
Absolutely. The project team needs to understand, consider, communicate with, and respond to the legitimate interests, needs, and opinions of all stakeholders. And effective and efficient engagement and communication involve figuring out how, when, how often, and under what circumstances stakeholders want and, perhaps more importantly, should be engaged.
It's not just blasting out newsletters then.
No. The guide suggests this moves beyond simple one-way communication to include awareness of the ideas of others, assimilation of other perspectives, and collective shaping of a shared solution. It's a much more dynamic, interactive, and inclusive process. This is especially important when a massive crane becomes a temporary and sometimes imposing landmark in a community. Keeping people informed about major lifts, road closures, working hours, that proactive communication can make a huge difference.
That deeper level of engagement sounds like it fosters true collaboration and trust, rather than just information sharing or public relations.
It really does. Engagement includes building and maintaining solid relationships through frequent two-way communication. It means actively encouraging collaboration through things like interactive workshops, face-to-face meetings where possible, informal dialogue, and knowledge-sharing activities. This helps create a sense of shared ownership and mutual respect among all parties involved, ensuring everyone understands the project's nuances, from the design choices to the complex logistics and safety considerations of a large crane operation.
And it seems like anyone involved can contribute to this positive dynamic, regardless of their formal title on the project org chart.
That's another interesting point from the PMBOK guide. It states that any project team member or stakeholder, regardless of their formal role or position, can potentially motivate, influence, coach, and grow the project team by blending different leadership styles, continuing their own skill growth, and leveraging various motivators. It underscores the idea that leadership and positive influence aren't just top-down, they can emerge from anywhere within the project ecosystem. This is essential for the kind of agile problem-solving required daily on a complex construction site.
So you can imagine a project meeting where diverse stakeholders, maybe the architect, the site supervisor, the crane operator's representative, a community liaison, are all actively contributing to finding a solution for a particularly tricky crane lift that might affect nearby residents, rather than just being informed after the decision is made.
Exactly. It's about leveraging that collective intelligence and fostering a sense of shared responsibility, truly shaping a better, safer, and more considerate outcome for everyone involved in and affected by the project.
Okay, and as anyone who's ever tried to build something, even just putting together flat pack furniture knows, things rarely go exactly according to plan. How do construction projects manage those inevitable uncertainties? Budget overruns, unexpected delays, material shortages, bad weather, especially when operating incredibly expensive and complex machinery, like large cranes, where delays can cost thousands per day.
Yeah, that's the million-dollar question, often literally. This raises the critical need for foresight and adaptability. Project success really hinges on anticipating, analyzing, and strategically responding to potential pitfalls, both in terms of time and budget, and crucially, ensuring the safety of everyone involved throughout. The CMAA Construction Management Standards of Practice outlines a structured risk management process that should be applied throughout all project phases.
So it's a continuous process, not just a one-off thing at the beginning.
Exactly. It involves systematically identifying potential risks and opportunities, assessing their potential impacts on project goals like cost, schedule, quality, safety, developing mitigation plans to reduce the likelihood or impact of negative risks, and then actively tracking these risks throughout the project. This is particularly vital for high-risk activities like crane operations, where the consequences of an accident can be catastrophic.
So it's not just about reacting when something goes wrong, like a sudden storm halting a critical crane lift, but actively looking ahead for potential issues, maybe predicting weather patterns, checking material delivery lead times, ensuring backup plans exist.
Precisely. A key part of risk mitigation involves assigning primary responsibility for specific identified risks to particular team members. This empowers them to develop and implement concrete action items with required dates to reduce the potential impact. This ensures clear accountability, for example, for ensuring the crane's mandatory maintenance schedules are strictly adhered to, or for meticulously managing the execution of a complex multi-crane lift plan.
And scheduling, as we discussed with CPM, is fundamental to managing time uncertainty. How do master and milestone schedules fit into this, particularly for coordinating huge pieces of equipment?
Well, the CM typically develops a high-level master schedule with the owner early on, outlining the overall project goals, major phases, and perhaps alternative approaches for phasing the work. Then, derived from that, a more detailed milestone schedule highlights key dates and events, especially critical design phase activities like 30%, 60%, 90% drawing completion targets, and procurement deadlines, like when bid packages need to be issued or when long lead items like specialized cranes need to be ordered or reserved. These provide crucial checkpoints to track progress against the overall plan and ensure that all necessary resources, including the right cranes and qualified operators, are available precisely when needed.
And on the financial side, how is cost managed proactively? Especially given the enormous expense of renting, setting up, operating, and maintaining large cranes.
Proactive cost management is vital. During the design phase, the CM provides ongoing cost management services, preparing various types of cost estimates that get progressively more detailed. Early on, it might be a parameter-based estimate, like cost per square foot. Later, it becomes a detailed unit price level estimate based on quantified materials. This ongoing feedback loop helps ensure the design stays aligned with the approved construction budget. It avoids costly redesigns later and allows for accurate budgeting of significant cost centers like crane rental, fuel, mobilization, demobilization, and operator wages.
But even with the best planning, changes happen. Unforeseen conditions, owner requests, that's where change orders come in, right?
Exactly. Change orders are the formal mechanism for documenting and agreeing to add to, subtract from, or otherwise alter the work defined under the original contract. Construction Management Jumpstart explains that they require a detailed cost estimate, usually including contractor overhead and profit, and must receive proper authorization, typically from the owner or architect, before the changed work proceeds.
And they often affect the schedule, too.
Almost always. Change orders frequently include requests for additional contract time, recognizing that changes inevitably impact both cost and schedule. This is especially true if the change affects activities on the critical path or requires replanning complex sequences involving cranes or other major equipment.
And there are also financial mechanisms built into contracts to incentivize proper completion, like retainage.
Yes. Halpin explains that owners typically retain or hold back a certain percentage, maybe 5 or 10%, of the progress payments due to the contractor throughout the job. This retained amount serves as an incentive for the contractor to properly complete all aspects of the project, particularly finishing those small, lingering punch list tasks at the very end. It's a kind of financial carrot.
And is there a stick, too, for finishing late?
There can be. Contracts often include provisions for liquidated damages. These are pre-agreed daily charges assessed against the contractor for each day the project finishes beyond the contractually agreed completion date. However, Halpin stresses that these figures must be a reasonable estimate of the actual damages the owner is likely to incur due to the delay, things like lost rent, extended financing costs, extra supervision costs. They cannot be arbitrary penalty charges, as courts have consistently ruled against punitive damages in contracts.
So it has to be a real demonstrable cost, not just a way to punish the contractor.
Yeah.
And finally, overarching all of this cost, schedule, risk is safety. When you have multi-ton loads swinging hundreds of feet in the air over a busy site, safety has to be the absolute top priority.
Absolutely paramount, non-negotiable. CMAA standards are very clear. Contractors are solely responsible for the safety and welfare of his employees and for the protection of property and the general public on their work sites. A comprehensive written safety program is essential. This must include specialized programs for specific high-hazard activities like crane operation, rigging, excavation, working at heights, etc., as well as procedures for things like environmental waste disposal and mandatory safety training for all workers.
And often there's a dedicated safety person on site.
Yes, larger projects typically require a full-time safety representative employed by the contractor, someone whose only job is safety oversight. And crucially, this person often has explicit stop work authority, meaning they can halt any operation, particularly a potentially dangerous crane lift, immediately if they observe unsafe conditions or practices without needing permission from anyone else.
That's serious authority. And as a specific example of how these management aspects tie together, the concept of float in a schedule, that leeway time we talked about for non-critical activities, CMAA notes it's often considered a shared commodity available to all parties, owner, contractor, CM. Decisions on how to use that float, perhaps to accommodate a minor delay or a change, should ideally be decided collaboratively by the CM and owner. It's a perfect encapsulation of the shared responsibility and coordinated effort required in modern project delivery, especially when coordinating the precious, expensive, and often critical time of a major crane.
Wow.
Wow. We've journeyed through this vast and fascinating history of building, focusing quite a bit on humanity's enduring quest to conquer gravity and lift things higher and heavier. From Vitruvius' idea of the holistic architect and Agricola's ingenious early water-powered lifting machines in the mines, through Palladio's proportional studies, the structural leaps of the Gothic builders, the revolutionary impact of steel construction in the Industrial Revolution, right up to the modern era of building information modeling, advanced sustainable design principles, and the incredibly sophisticated project management needed to orchestrate it all.
It's been an incredible overview of human ingenuity, hasn't it? Always pushing the boundaries of what we can lift, what materials we can use, and ultimately what we can build.
So what does this all mean for you, the listener, the learner? Well, it means that every structure you encounter, no matter how simple or complex, is really a testament to this ongoing human endeavor to overcome fundamental challenges. And central to so many of those challenges, particularly for the modern marvels that define our skylines, is the power of the crane and the knowledge required to use it effectively. Building is this profound blend of art, science, engineering, and meticulous coordination. It's a story about our enduring quest to overcome gravity, leverage materials both old and new, and orchestrate people and powerful machines to transform abstract ideas into tangible, functional realities. The history of construction, in many ways, is the history of human problem-solving and collaboration, often literally reaching for the sky.
A continuous striving to build better, safer, faster, and more efficiently, often driven by our ability to lift more.
So here's a final provocative thought to leave you with. Considering how much our built environment has evolved, with digital tools enabling buildings to be designed and constructed with unprecedented precision, and with cranes capable of lifting components weighing hundreds, even thousands of tons, and with this idea of smart buildings on the horizon, potentially learning from and coexisting with us, what new responsibilities do we take on? As citizens, as occupants, as professionals involved in the build world, what responsibilities do we have to ensure these increasingly complex structures and the powerful machines that build them truly serve humanity's highest aspirations for things like sustainability, community well-being, and the quality of the human experience itself?
That's a big question.
It is. It's a future we're all, in some way, building together one careful lift at a time.